In this video, we will calculate the pH of a solution when that solution contains a salt that is the conjugate acid of a weak base. Generally, these are a little bit harder to recognize. So ammonium is a very common salt cation, and this is ammonium chloride. So it does dissociate into the ions, and ammonium is the conjugate acid of ammonia, NH3. So chloride is the conjugate base of the strong acid HCl, so the chloride ion will not affect pH. But the ammonium ion, this is the conjugate acid of the weak base ammonia. So this, because it's positive, the positive cation, it's going to act like a metal, and it will make the solution acidic. And so the same steps are going to be helpful, and that would be to write this ion with water. So if we write NH4 plus and HOH, what's going to happen here is this is a conjugate acid, so water is going to act like a base and be a proton acceptor here. So we'll end up with H3O plus NH3. And so this is the acidic hydronium ion. And so step one, we write the reaction with the ion with water. And again, as a reminder, because this is positive, we're going to have a positive ion on the right-hand side of the reaction. So in acid-base chemistry, we either have H plus, which is really the same as H3O plus, or OH minus. So then second, we have to calculate the Ka for this. So this is equal to the water's equilibrium concentration over the Kb for ammonia. So we have to look up the NH3 value, our dissociation constant. So ammonia has the Kb value of 1.8 times 10 to the minus fifth. So the ammonium ion will have a Ka value, which is the Kw divided by 1.8 times 10 to the minus fifth. So if we calculate that, negative 14 divided by 1.8, negative 5, that Ka value, that's relatively small. So this solution should not be very acidic, probably in the 6 region, 5.5 times 10 to the negative 10. And I'm going to leave this number in the calculator. And if we take that and write the equilibrium expression, this is dissolved in water, AQ. This is a pure liquid, so it does not enter into the expression. This is AQ. This is also AQ. So we'll have this 5.5 times 10 to the minus 10 equals x squared over the concentration of the NH4 plus. Okay. And in this problem, I failed to give us that example. We'll assume that we have a 0.12 molar solution of ammonium chloride. It's the same as the salts that we were using in the previous videos. So we set this equal to x squared over 0.12, and I'm going to leave this number in the calculator and multiply both sides by 0.12. Take the square root of that. So here x equals 8.16 times 10 to the minus 6. And here x is equal to H plus, or the hydronium ion shows up here. So I just take the negative log of this value, take the negative log of second answer. So here the pH is 5.09. So that's considerably lower. I was thinking it would be in the 6 range. So the pH is going to be 5.09, and that should make sense that it would be acidic. That's because the ammonium salt, because it's the conjugate acid of the weak base ammonia, we will see that the pH would not be 7 in water, but the pH would be less than 7 or acidic. I'm going to do one more example with a different salt. These are hard to recognize, so it requires that we remember some chemistry that we've had before. There is another salt, so let's do another calculation. Calculate the pH of a we'll say 0.15 molar solution of methyl ammonium nitrate. And so this would really constitute the ion, and then nitrate would be like that. This is used as an explosive. So anytime we see a nasty formula like this, we want to look for an NH group. Here we're going to have, well, this actually won't have a lone pair on it, but the nitrogen is a clue that we're looking at for conjugates of weak bases. Okay. So this has the formula, a methyl group, a carbon with 3 hydrogens around it, and then nitrogen is going to have 4 atoms bonded to it. So that is going to make this whole complex here positive. So that's the methyl ammonium ion, and then the nitrate. So we have a +1, -1, and so that's what our salt is. The nitrate will not affect pH because nitrate is the conjugate base of the strong acid, nitric acid. So that will not affect the pH. This will. And so what we're going to do is look in the book for the base. The conjugate base of this will have 1 less hydrogen. So the relationship between a conjugate acid-base pair is a proton. So we're going to find this NH2. So this is actually a weak base, methylamine, and we'll find that on our KB table. So right here, methylamine, CH3NH2. So that base is a little bit stronger of a base than ammonia. So its conjugate acid, the methylammonium ion, is going to be, what did I say here? It's a stronger base, so the acid will be, should make the solution less acidic than the ammonia. Of course, I changed the concentration, so we won't really care about that. But if we look here, the KB for this from the table was 4.4 times 10 to the -4th. So what we want to do is recognize the ion and recognize the weak base, so that we have the conjugate acid-base pair. So if we write this with water, CH3NH3 plus in the presence of water, we're going to end up with something plus over here because of that positive charge. So we've got water. What's going to happen is water in the presence of this acid, water's going to act like a base and accept a proton from here. So we'll end up with H3O plus. So here's our acidic hydronium, and we'll leave behind methylamine. Oops, it's supposed to be NH2. And this is our base, methylamine. Okay. So if we write the equilibrium expression for this, Kb equals the H3O plus. Sometimes I get lazy and just put X squared, but that's what that's going to turn into, all over the concentration of the salt. So this turns into an x squared divided by the initial concentration of the salt, which is 0.15. So all I'm going to do is solve for x and take the negative log of x. And again, in this case, x stands for the H plus, or more formally speaking, the H3O plus. Okay, so we'll turn this back on and calculate the Ka value for this. This should be a Ka. So anything positive technically could be acidic. So the Ka for this is 10 to the minus 14th over the Kb value, which we looked up in the table. So that's over 4.4 times 10 to the minus 4. 14 divide that by 0.4 times 10 to the minus 4. Oops, before all that. Negative 14 divide by 4.4. negative 4. So my Ka value is relatively small. 0.27 times 10 to the minus 11th. This equals x squared over the initial concentration. So I'm just going to solve for x. And remember that x is equal to H3O plus. So when I want the pH, I'm just going to take the negative log of that value. And it's best to leave all this in the calculator instead of truncating that number. So I'm going to multiply by the denominator to clear that denominator. Then I'm going to take the square root of that number. So my x, or my H3O plus concentration, is 1.85 times 10 to the minus 6th. And that doesn't sound right, does it? Oh yeah. Take the negative log of the second answer. Yeah, makes sense better. So the pH here is 5.73. And again, the conjugate acid of a weak base, when it is in the form of a salt, the positive ion will make the solution acidic as long as the anion of the salt is the conjugate of a strong acid. So in our class, we're not going to have to calculate the pH when we have when the anion is the conjugate of a weak acid and the cation is the conjugate of a weak base. It can be done, but that's more than we need to do. And if we look here, this is not that much lower than 7, but the conjugate acid is introduced into the solution, not from base, but the conjugate acid is the cation in a salt.